All right, so here in lesson 2.4, we are going to be going through what we call the sum and difference formulas. Saying each of our big three trig functions, sine, cosine, tangent, all kind of have their own formula, so to speak. These are not ones that I'm necessarily going to ask you guys to memorize by any means. Say they are on that unit circle sheet. They are in the bottom left-hand corner, so I have that front side. So there's three of them. So like I said, one for sine, cosine, and tangent each. And so what they kind of allow us to do is to evaluate angles more accurately that maybe aren't directly on our unit circle. Okay, because obviously the unit circle doesn't hit every single possible angle. So this kind of opens the door for some other ones where we're not necessarily just settling for the decimal accuracy of a calculator. We can get a little bit more accurate, even though our answers might not look real pretty, say with how they're going to end up, but it does give us a little more accuracy. So if we kind of write each one separately, there would be 6 of them, just because there's a difference if you're adding two angles together or subtracting. The nice part with each of these is they kind of follow the same pattern as far as like sine with addition of two angles and sine of subtraction with two angles kind of follows this same pattern of like sine, cosine, cosine, sine. Whether it's adding, subtracting, it still goes sine, cosine, cosine, sine. And these, technically they're alpha, beta, those symbols are just angles that we're, say, adding together. So we're going to either have those in our problem or we're going to be able to find those pretty darn easily. The nice part with sine, I would say, is this sign here in the middle. So if we're adding a plus b or alpha plus beta, then we have addition in the middle here. If we have subtraction, then it's subtraction in the middle. Everything else is the same between sine of a plus b and sine of a minus b. Okay, it's the same pattern. Cosine is kind of similar in that whether it's adding, subtracting, it goes cosine, cosine, sine, sine, cosine, cosine, sine, sine, with alpha, beta, or a, b, whatever you want to call it. The difference with cosine is if we have addition in the middle here, then it's subtraction over here. So it's kind of backwards, because if it's subtraction over here, then it's addition over here. Okay. And then lastly, tangent looks kind of different because now we got a fraction here and we got tangent being used all over the place. As far as like signs, positive, negative, stuff like that, if it's tangent of a plus b, then it's adding on top, subtracting on the bottom. And if it's subtraction here, then it's kind of opposite, where it's subtraction on top, addition on the bottom. Okay. How that's going to look on your unit circle sheet, rather than writing all 6 of them, we try to condense it into 3 just to maybe save a little bit of space, a little bit of writing. But how they kind of try to represent this is if you take a look at like this plus minus sign here, whatever the top sign is over here. So if it's addition on top over here on the left, where it's say addition over subtraction, then that top sign over here corresponds with the top sign over here. So it's plus, plus. And if we look at like cosine, if I have addition on top here and subtraction on top over here, that's how they try to represent kind of the oppositeness, I guess, so to speak, of cosine there. Okay, but it's still that cosine, cosine, sine, sine. So that part is all the same. And then kind of same thing with tangent, where if I have addition up here, that matches with the addition and then subtraction in that bottom one. Okay, so if we actually put some numbers with this, okay, if we go through a couple examples, and I'm hoping it's okay that I already kind of have problems written out just so that I could hopefully limit any silly mistakes that I have here. But if our first example, we've already kind of got our angle split apart into maybe 2 smaller ones, okay, because if we did this 135 minus 30, this is basically asking us to find cosine of 105. Which cosine over 105 is not on our unit circle, so we wouldn't be able to use our unit circle or evaluate it accurately if we just have that at our disposal. But if we split that 105 into 135 minus 30, say then we could use that cosine u minus v thing here, and I kind of tried to rewrite it so you don't have to necessarily flip back and forth, but that's going to turn into cosine u cosine v minus sine u sine v, where u is just the first angle and v is the second one. So in this case, u is going to be 135, v is 30. Don't worry about like this negative sign like going with the 30. We can just take v as a positive 30 in those cases. Okay, our formulas kind of account for that subtraction sign, so we can just take v as the positive angle there, which makes it a little bit easier. But then if we plug in the 135 for the u here and here, the 30 in for the v there and there, we get kind of at start a little bit of an uglier looking thing, because now we got like 4 trig values in there. But if we're able to break it into 2 angles that are on our unit circle, we're going to be able to evaluate all of these things. Okay, we're going to be able to take cosine of 135, look at our unit circle, and see that that equals negative root 2 over 2. And we can take cosine of 30, see that that equals root 3 over 2. And then same thing with sine of 135, that's where we're getting, say, the root 2 over 2, and then say our sine 30 is giving us the 1/2. So we're able to replace all of those trig functions, so all of our sines, cosines go away. We're able to plug in just regular numbers, even though they might not be nice looking numbers with all of our square roots and stuff. But we can then simplify that. So we can take the negative root 2 times root 3, and to do that we just take the 2 times the 3, and that's where we're getting the root 6. Negative because it's negative times a positive. Then our root 2 times 1, say this part here is giving us our root 2 right there. And then the nice part is, because we're having to multiply the bottom 2, so those 2 times 2 get us the 4s. The nice part is we already have a common denominator between these 2 fractions. So then we can combine these 2 fractions into one fraction of just negative root 6 minus root 2 over 4, which that is about as pretty as we're going to be able to make that, because we can't like divide everything by 2, even though 2, 4, and 6 are all divisible by 2. Those square roots kind of prevent us from doing that. And if we were to like take the square roots and turn them into decimals and try to combine those 2 on the top, that kind of undoes or kind of defeats the whole purpose of trying to keep our accuracy and avoid decimals to begin with. So like I said, we're not going to make our answer real pretty, but it is going to give us maybe a little bit more accuracy than what a calculator would be able to. Okay, and for the sine and cosine ones, a lot of your answers are going to look very, very similar to that with the root 6, the root 2, and the 4, because a lot of these times we're going to try to break it into angles that are on our unit circle, and unit circle values just kind of repeat over and over with the root 2 over 2, the root 3 over 2, the 1/2. It's just which ones are positive, which ones are negative, and kind of how you're utilizing those. Okay. So if we skip a couple here and jump to stuff that's going to look really similar to the assignment for this, rather than already having them broken apart into like the 135 and the 30, so you're just going to have like sine of 15. Saying the first thing you're going to have to do is figure out what are 2 angles from the unit circle that we can use to add or subtract to get to this original, say, 15 degrees. And now there's a bunch of different ways that you could do that. Personally, I like to try to keep the numbers as small as possible. Just make it a little bit easier maybe in that way. So I just went 45 minus 30. Again, do you have to use those 2? No. Could you have done like 135 minus 120? Yep. Could you have done 150 minus 135? Yep. So there's a bunch of different ways that you could break those down or kind of break it apart. But if we go with the 45 and the 30, sine of u minus v, say, is up here. And so that goes sine of u, cosine of v, minus cosine u, sine v. And again, u and v are just the angles here. So we got u is 45, v is 30. So if we plug that in, we get sine 45, cosine 30, minus cosine 45, sine 30. And again, once we've got all those plugged in, we can go to our unit circle, find sine of 45, that's our root 2 over 2. Cosine of 30 is root 3 over 2. Cosine 45 gets us the root 2 over 2, and then sine 30 gets us the 1/2. And then again, if we multiply, say, kind of all these things together, root 3 times root 2 gets us that root 6. The 2 times 2 gets us the 4 for that piece. And then root 2 times 1, again, 2 times 2 gets us the root 2 over 4. which, like I said, sine, cosine, your answers are going to look very similar because, again, we're using that root 6, root 2. We're just kind of squishing it into one fraction where it's all over that common denominator of 4. Okay. Where it does get a little bit different is if we start dealing with tangent. So if we've got tangent of 75, again, there's a few ways you could get to 75 degrees, whether you wanted to add, whether you wanted to subtract. Again, it doesn't matter. You should get the same value in the long run. So personally, I just went 45 plus 30. So that's the first combo that came to mind for me. And so if I'm going to roll with 45 plus 30, I would need the tangent of u plus v, which would break into tangent u plus tangent v over 1 minus tangent u tangent v, which again, u is just the 45, v is the 30, so I'd end up with tangent 45 plus tangent 30 over 1 minus tangent 45 times tangent 30. And if we then, again, kind of use our unit circle, replace those things, tangent of 45 is just a regular old 1. Tangent of 30 is root 3 over 3. And then on the bottom, we get the 1 minus, again, tangent 45 is 1. Tangent 30 is root 3 over 3. And so if I can maybe show one kind of little step in here, just because this is something that gets quite a few kids. Say that top part will just keep 1 plus root 3 over 3. But then on the bottom, a lot of times I'll see kids try to do this part first. They just work left to right. And they do the 1 minus 1 is 0, or maybe it's 1 plus 1 and they get 2. But PEMDAS says we have to do exponents first. Or not exponents, multiplication first. So we'd have to do this 1 times root 3 over 3 first. So if we do that, we end up with 1 minus root 3 over 3. So that's kind of an intermediate step there just to, again, make sure we get our order of operations right. But then to simplify this thing here, ideally we want to get rid of the fractions inside of fractions. So what we can do is change these ones, okay? Because changing 1 is not incredibly difficult, okay, without changing the value of the whole thing that we're working with. Because we could turn those into these 3 over 3. Okay, because anything divided by itself is 1. So those don't change value at all, but it gives us a common denominator now between all of these different fractions. So I got denominator 3, 3, 3, 3 between all the little fractions. And with some, I guess, mathematical magic, kind of skipping a couple steps here, basically these 3's can all cancel each other out. And so then I'm just left with 3 plus root 3, which is where that top part is coming from, over 3 minus root 3, which is where that bottom part is kind of coming from. And for me, that is as simplified as you need to take it. I know some people would argue that we shouldn't have a square root in the denominator of a fraction. I would argue that at a certain point in math, it tends to be less like frowned upon, I guess. Like having taught calculus a couple times, we have square roots and denominators of fractions all the time. So I'm going to say if we're okay with it there, we're going to be okay with it here. Okay. So again, not a pretty looking answer, but it is a more accurate one than what our calculator would give us as a decimal. Okay. And so if you're dealing with a tangent addition or subtraction one, your answer is going to look really similar to that, where you have like 3's and root 3's. Or maybe it's a 1 plus root 3 over 1 minus root 3, something like that. Where it almost looks like it should be the same on the top and the bottom, but there's like one sign that's maybe different. Okay. So that's kind of going one way, where we're taking sine or cosine or tangent of an angle and breaking it into different ones to kind of evaluate it. If we wanted to go the other way around, so if we had something like cosine 30, cosine 20, minus sine 30, sine 20, and we want to get it like simplified into just sine or cosine or tangent of just an angle, we can do that too. So we can simplify it and condense it. And so with these, first thing I'm looking at is what's the pattern of like sine, cosine, cosine, sine, or cosine, cosine, sine, sine. And so this first one goes cosine, cosine, sine, sine, and that is the pattern of a cosine addition or subtraction, or sum or difference formula. So that part is telling me that it's going to be cosine of something. And then this 30 and the 20 are the u and the v, essentially. So here's u, here's v. And again, I kind of know from the formula that cosine, these signs are opposite. So if I see subtraction here, I know it should be addition here. So that's how I know it's cosine of 30 plus 20 versus 30 minus 20. And then we could do the 30 plus 20 and we could get cosine of 50 for an answer. Okay. So if we look at kind of a different one, so if we go sine, cosine, cosine, sine, that's your pattern of like a sine sum or difference formula with, again, u and v. So I've got u, v. But again, with sine, this one and this one kind of match up. So if it's minus here, it should be minus here. And if I go 10 minus 40, I get sine of negative 30, which a negative angle is perfectly fine. So we can get that. So we've had plenty of negative angles within this class, so it's nothing super, super crazy there. Okay, so we can kind of go both ways. Okay, so we can take it to try to evaluate something, or maybe we can simplify to get more a condensed, more efficient form of an angle as well. Okay, so that's the kind of highlights or the main things from lesson 2.4. So there's a couple identity questions kind of within that assignment as well, but this is the majority